Hi, Kunle. Thanks for joining me today for my next Wave speaker series. As you know, this is a speaker series where I want to talk to inspiring leaders in the area of startups, entrepreneurs, and CEOs that can be able to, inspire next generation leaders. So thank you for joining me. Well, let's start with a little bit of your background because I don't know whether everybody knows you, and you have so many different things you're involved. As I'm speaking and spending more time with you, I'm learning about your background. The professor, well-known computer architect, and then I'm learning that you've done multiple startups, and one of them that I was involved as an investor, but also you're also involved in Stanford athletics program. So if I ever want to get a football ticket, I think I better contact you.
Yeah, I mean, I sort of developed over the years. I've always been interested in sports and athletics. And when I was younger, I was not that good at playing soccer, but I like to think that it was something that always interested me. And, since coming to Stanford, I've been really impressed with the ideal of creating student athletes, right? Of integrating the students who are, focusing on their individual sport, but not having them segregated and having them integrated with the rest of the student body. And of course, all the students that we have at Stanford are superlative in their own right, and so that was something that really attracted me. And then there was a combination of my desire to get involved with Stanford athletics and helping doing recruiting for the football team, and so that is how I got involved in becoming a faculty athletic fellow to the football team, and I talked to many incoming and existing football players, and some of them work in my research lab during the summers, and we've got a wide range of interests. And I remember one especially interesting recruiting year where out of, I think, 20 recruits, 4 or 5 of them were interested in majoring in computer science. And so that's the sort of caliber of athlete that we get. And so it keeps it very interesting.
Yeah, that's really great. I mean, of course, when I was going to school, I was also in athletic programs. And I really believe and embody the idea of sports and academics combining, make it better person, in my view, because you learn so much from sports and discipline and the focus and being able to earn it as a way to train and working as a team. There's so much lessons that you can learn from that. I'm a total believer of sports and athletic and academic programs in combining. And I think what you're doing is great. Wow, 5 students out of football players. That's amazing.
Yeah, no, and we both come from sort of international backgrounds, and we know that the way that America, combines higher education and athletics is unique in the world, right? No other place does it. I grew up in England and Nigeria, and they certainly, you decide early on whether you're going to be an athlete or an academic, and never the twain should meet. And I think it's really great, as you say, that you see how focused and disciplined and hardworking these student athletes are, and it's a great tradition.
Yeah, it's on the top of your normal schoolwork, having a training that are 4-5 hours a week, and the top of that, you got your weekend competitions. It does, give you extra load, but it gives you ways to manage your time better. So when you are actually coming out of school, you're much better prepared to manage multiple tasks and being able to deal with the competition and dealing with different challenges in life. So great program. You're right. Coming from my culture, Korea, if I play sports, I better go to different school in a sports program, not combining two. So that was the best thing that happened to me coming to USA, actually.
Yeah, great. No, it's a very interesting how one's what happens in life and sort of how it kind of dictates your future. And you asked about my background, and I mentioned I was born in the UK, and I left for Nigeria when I was 11. And it was interesting because I ended up going to a school in Nigeria that was run by Americans and was run on the American system. And by all rights, I should have come back to the UK for university because I was British citizen. It was free university education at the time. But because of the school that I went to for high school, I didn't have the requisite what were called ordinary and A levels required. So I ended up coming to the United States, and that, of course, set me on a different direction that I think has been, much better than might have happened had I gone back to the UK.
Well, that's the gain for America, I guess, for Silicon Valley, for you to land over that direction.
Yeah.
So let's talk a little bit about some of the companies, and particularly, I think we can talk about SambaNova because it's a company that I was involved with you, and that's how we met actually. And as a professor at Stanford, and being able to drive your computer architecture for a long time actually, and then. And it's driving one of the most important AI accelerating system company that came out from Stanford, as well as the local Silicon Valley teams. So maybe you can talk a little bit about your journey, about startups and SambaNova in particular, for the audience that may not know much about you.
Yeah, so startups have been something that, when I started as an assistant professor at Stanford, I was not focused on. I was focused on kind of developing ideas in computer architecture. But being at Stanford and being in the Valley and seeing how luminaries like John Hennessy had kind of translated their research into to companies gives you inspiration about following the same path. And when we did the early work in single chip multiprocessors, I think the industry was, the existing industry wasn't really ready to embrace those ideas. And so that was some of the impetus to, transferring the technology directly by doing a startup, because we wanted to prove something. Hey, these are really good ideas. These are ideas that could transform the industry. And so, much later when we were thinking about how to transform the whole world of AI, of course, AI is transforming the world. I always think of the picture from Andreessen of the sort of software eating the fish, software eating the world, right? You can think of the software fish being eaten by AI, the AI fish, which is even bigger, right? Because it truly is transforming the world of software and everything else. And so working with Chris Ray, who's another co-founder of SambaNova, we developed these research ideas around what one would do to both change the algorithms such that they could be more efficient, and then build architectures that would execute those algorithms very efficiently. And the whole idea revolves around this idea of data flow, right? Which is actually the natural way that you want to execute these machine learning, deep learning algorithms, because they essentially are graphs of operators, right? The operators could be matrix multiply, they could be convolution, they could be pooling, and the connections between them. And if you look at conventional architectures, they don't focus on optimizing and programming the movement of data, right? And as we all know, when it comes to computing, 99% of the power that you expend is actually, moving data around, right? And so if you could optimize that, then you could get lots of efficiencies that conventional architectures are not exploiting. And, the nice thing about, as I say, these machine learning models is they naturally give you the data flow, right? It's there for the taking. So you should look at that and say, how can I take the description of the models as presented and compile that into something that's very efficient at moving data around so that I can get efficient computation, so that I can get minimum energy usage, and so that I can minimize my use of memory bandwidth. And so that was kind of the impetus.
Right. So Kunle, if I think about this whole concept, right, the traditional architecture where I started working at Intel was very instruction set heavy and was very compute driven. Now looking at the way the data stream is happening today, which is there's so much data that are doubling every 2 years, pretty much, with the unstructured and structured data coming all together. Now, what's the more efficient way of processing all these data? And this is where your approach of new architecting, that can be data flow architecture that you're working on. And the idea of data flow architecture isn't about just hardware, software, it's coming together, right? Because you need both of them. And this is where what you're saying, that it's not about software 2.0 eating the world, but it's about that. It's about the AI eating the world, because it's a system. It's a new approach of doing both software and hardware.
Right. Absolutely. It is about combining software and hardware and understanding what is required for the applications and what kinds of software can best meet the needs of the AI applications, and then how you marry that software to architecture, VLSI systems in an integrated fashion in a vertically optimized environment. And that was the genesis of SambaNova. SambaNova was designed to be this very vertically integrated company that looked across the stack from the applications and even services on top of those applications, and then how you could drive those use cases to the underlying software models and the way in which those models are optimized and compiled to run on new systems architectures that are efficient for these kinds of things. And so, it's sort of, how do you provide AI for the enterprise in much the way that kind of Apple provides this integrated software, hardware, services component to consumers.
So the acceleration means really in a way, there is a traditional compute that has been growing through more slow, but there's only so much you can do with that architecture. So there is a whole new accelerator that are coming from this new approach of managing the data flow and smarter network process design with a faster backbone. And then you are adding on the top of that, the software layer that are being able to give scale out capabilities, right? That can give you the new system capability that are much bigger power than traditional capabilities, probably millions more power. And I think it would be good to talk a little bit about where does this new engine SambaNova is developing, which is a system now, because you're doing the whole layer of compute on the top of that, accelerate, and then with the software layers on the top of it to enable this transformer capabilities. And tell us a little bit about where is the application that would make sense, and what are some of the progress that the company has been made? Because I know you're working there as a CTO and you're spending time along with your Stanford duty.
Yeah, so I mean, I think if you look at the whole AI, ML computing space, especially the natural language processing, what you see is, bigger models are more capable. The models that, recently be introduced by OpenAI are the GPT-3 model of 175 billion parameters. And you look at the growth of these models, growing at the rate they're doubling every 2.5 months, right? So clearly this is unsustainable in the sense that you need to be clever about how you continue to improve the quality and accuracy of these models. But the models are very big and they require huge amounts of computing capability and also memory in order to get to be able to run these models, and they are beyond the reach of all but the largest organizations, right? And so part of what we're doing at SambaNova is to make it possible to run these huge models with much less resources, much more efficiently, and this puts this capability within the reach of of research organizations, banks, and other places that are not the big hyperscalers. So you can think of this as sort of, somewhat of a democratization of this huge capability provided by these large AI, ML, natural language processing models. And so that's one of the things we're doing, is how do we enable, very, very large models with very large language models with high capabilities. Another thing that's also possible with the sorts of capabilities that we're doing is the ability to train models for high resolution, what we like to call true resolution images, right? So when you're talking about, you want to look at mammography, medical imaging images and build models based on that can detect cancer earlier, small cell cancer earlier, or whether you want to look at the sort of images that are created from astronomical data and detect, the sorts of things that the astronomers want to understand. Building these models, we can build these models that are the full resolution of the image, so you don't have to divide the image up or lower the resolution, which means, of course, that the models are more accurate. They are able to detect things earlier. They're able to detect objects that the previous models could not, because either they had to lower the resolution or divide the image up so that you could run them on conventional architectures. So these are the two of the key areas that we are developing in terms of the model capability, and it's enabled by this new data flow architecture with much bigger memory and much more efficient processing.
So the benefit really with your new approach is being able to see the whole data much clearly, because you can see a bigger set of data, whereas traditional compute, you can only look at it segment at a time, because their ability to swallow the data is limited based on their bandwidth and their compute capabilities. And that gave you a much better power. Yeah. And
exactly, right. So you have two choices. You've got a limited amount of memory, you've got a big image. Either you could slice the image up, right, and get smaller patches, and then of course you miss what happens at the boundaries, or you could lower the resolution of the whole image, and now the whole thing is blurry, right, and the model is less accurate, right? So and we give you the ability to look at the whole image in one fell swoop, which is a tremendous advantage.
Because when you look at the data segment at a time, you may lose the graph, the relationship in a whole set. And I think that's really important data interaction, right?
Yeah, you can imagine, if you're looking at an image and the important part of the image actually crosses several of the boundaries that you've segmented your image into. Now you're going to, first, developing labeling an image of that sort is going to be difficult. So even training a model is going to be difficult. And then the model is going to be fundamentally less accurate because it's only looking at a piece of the data in each instance. And so the ability to look at the whole image is providing tremendous benefits in the medical imaging and the large astronomical imaging and scientific, many scientific problems, in fact, come down to high resolution images. And so if you're doing X-ray imaging, if you're doing manufacturing inspection, again, this all comes down to being able to build these accurate, true resolution image models.
Or fraud detections and anything you want to look at, a lot of data that are moving in correlations among those. Let's talk a little bit about this generative pre-trained transformer. 3, because I think people talk about it, but I don't think that many people understand what that means. And I think it has huge implication to how we look at the data. And clearly transformer changed the way machine learning happens from supervised learning to unsupervised learning. So maybe you can talk a little bit about the journey for the people that may not know too much about this.
So GPT-3 was a model that was developed by OpenAI, which was originally funded by Elon Musk, and it stunned the world, because it was a pre-trained model trained on most of the data on the internet, and it is, so it has impressive language generating capabilities, and it has 175 billion parameters and costs about $5 million to train. But the problem is with that model is that it was trained on generic data on the internet, right? So if you're a business that wants to use it in a bank on some sort of financial application, right? So maybe you want to do financial fraud detection, or whether you want to help your customers with some automated responses to their banking questions. It may not necessarily, be the best thing. What you really want to do is you want to take that backbone pre-trained model and you want to optimize it and specialize it for your particular task by doing what they call fine tuning or fine tune based training. And so we at SambaNova give the ability both, to train the original large GPT-3 model, but also more importantly, to dramatically increase the accuracy on your particular problem or your particular application by doing this fine tuning, which also requires huge amounts of memory and a lot of computing capability. So
in the world of technology, sometimes we use this word for giggle, right? Garbage in, garbage out. And so what you're training is really critical, right? And what you're describing is generality versus the speciality that are required for specific solution and specific problem that you want to solve. And they are the right data matters a lot.
Right.
Yeah. Mm-hmm. Very interesting. So now you also done other interesting companies. I remember talking with your co-founder, Migo, which is a African fintech company. So for the audience, maybe you can talk a little bit about the scene of African technology world and what's happening there and what's exciting, and tell us also a little bit about what Migo is trying to do.
Yeah, well, I think there's certain areas of technology where you could say that Africa is ahead of the rest of the world, right? And one of those areas was kind of mobile finance, right? So you think about what was happening in Kenya. About 10 years ago with M-Pesa, and then being able to use this idea of mobile money to move, to actually transact, and people were both sending money and buying goods and services purely using their mobile phones. And this is long before it was happening anywhere else. And so, but of course, Africa is many different nations, and different countries have different rules and regulations. And in the country that I'm most familiar with, Nigeria, you have both, of course, mobile telephone companies, and you also have the banks, and they are very separate. And so what we did with Migo was based on technology that was developed at Stanford, which was a very efficient platform for doing machine learning, was to say, okay, how could we be an intermediary between the telcos who have lots of customers and the banks that want to actually provide loans to those customers, but can't do it in an efficient way given their traditional loan processing mechanisms and their traditional credit risking environments. And so we came as we've got this platform that knows how to consume lots of data and build efficient ML models. Can we use mobile phone behavior to credit risk individuals for small loans, right? And so that was the idea, was to come in and provide this technology layer that would provide this capability of credit risking individuals, providing, and then put a service layer on top of that which would actually deliver the loans over some sort of payment rails. And then also provide collection services. And so one of the things that you find when you go into developing nations is that it's not enough to come in with a core technology and imagine that you're going to fit it in and change the way that things work. You often find that you've got to build up a whole set of infrastructure that enables your technology to actually demonstrate its usefulness. And so that's what we had to do. We became.
That's a great example of using mobile data and solving the problems of the microfinancing that are needed. So many people don't have a bank account, but they do all have mobile phones. So using the mobile credit to enable the new financing capability for lending or micropayment is a wonderful way of creating an example of application. It could work in insurance, it could be in other industries too. So that's interesting how the let's say the necessary can create the invention, right? So this is an example of that.
But again, it's an example sort of how technology invented in Silicon Valley can, with the right sort of catalysts and connection, translate to places far away from Silicon Valley. And in this case, technology that was developed and honed in the developing economy of Nigeria is now being translated to South America and Brazil, and starting to be looked at to being deployed in other places in Asia also. So it was a very interesting example of sort of how ideas that developed in the lab, get refined in real environments, real use cases, and then the technology gets to the point where it can be applied, in many different locations.
Yeah, I mean, the idea came out of Stanford, getting deployed in Africa and then Brazil. And who would expect that? I think that kind of new approach and innovation is probably going to happen even more than ever before because of the availability of mobility and cloud. And the business model is transforming the all of us very quickly here. So as you're looking at your innovation.
And I think your point is really well taken, that it had, all these things had to come together, right? The cloud had to be there, the mobile piece had to be there, the Stanford technology had to be there, and the entrepreneurs who kind of, knew the local landscape had to be there. And then once you bring all these things together, all of a sudden, then you get,
Here it comes. What was the most difficult part, if you recall, example, Migo, and you get that going? What were the challenges you have to solve?
I think, the challenge is always with, dealing with an environment like a developing country like Nigeria. That's the challenge. Things are not necessarily straightforward. We can go into all kinds of details, but you have to be able to, my co-founder, Ekechi Waka, was on the ground, and he had to figure out how to, navigate between the banking industry and the telco industry and the payments rails and the different government regulators and for trying to figure out all these things. The technology was easy, at least, compared to all those things that one has to do to actually make the company successful.
It's a friction you have to manage to make it work.
Yeah.
So totally understand, especially when you're dealing with data, when you're dealing with payment, when you're dealing with telecom. I mean, these are all highly regulated industry with super monopolistic power, right? So have them talk to each other as a middleman in between, that's not easy.
Yeah. You absolutely, you got it. Yeah.
Well, very good. Let's talk a little bit about what you're teaching nowadays at Stanford.
So I'm teaching parallel computing. So it's a course in which students learn how to write programs that work efficiently on modern computers, right? And modern computers are composed of multiple microprocessing units, as you know, right? And if you go back in time, right, to the early 90s, my research was all about how to, make the idea of what people now call multi-core reality, right? And back then people thought it was a strange idea that was not worth pursuing, but we pursued it anyway because we wanted to do something that we thought was the right direction. And now, of course, we're at the point where not only are the processors multi-core, multi-thread, but they also have the ability to execute SIMD or vector capabilities. And so what we do is we teach students, how do you write code that runs efficiently on these machines? How do you a lot of CS is about, getting the functionality and algorithm correct and thinking about asymptotic efficiencies. We focus on sort of how do you get performance on and make your application run as fast as possible. And we show that, between something that is naively written for a modern CPU and something that's optimized can be, two orders of magnitude in terms of performance. So that's a lot. And so once students see that, their eyes are open to the possibilities.
I mean, I remember my early days at Intel when the microprocessor x86 architecture was getting developed from 386, 486, the Pentium. It was all about big chip with a lot of power going in there. And to go get the performance, you have to get up the frequency, which means it creates even more power. And the density of the power was a real issue. So you have to put cooling system all around it. But actually, I think what you're working on at the time was people are not looking as seriously, but you were actually imitating our brain, right? By processing things in parallel, just like our brain does, which is a lot less power in each core.
Yeah, exactly. That was the whole approach. Is sort of how could you do things more efficiently by doing things in parallel, and much like biological systems. And I remember the first startup we did pitching this to Sandhill and saying, look, hey, I talked to the founders of Google and Yahoo, and they're running out of space and power in the data center. This is an approach to processing that could give you an order of magnitude in terms of power efficiency for these problems that were naturally multi-threaded, right? So you think of all the requests coming into a data center, and you have natural parallelism there, right? I always say, take the easy path, right? Going back to our earlier conversation, hey, if machine learning applications give you data flow, then you should build a data flow processor. If data center applications give you lots of request parallelism, then you should build a parallel processor, because that's going to be the thing that's most efficient.
Yeah. So as a pioneer developing this parallel compute and then being able to see where we are today, clearly now there's no debate. Clearly everything is multi-core, everything is multi-thread, everything is concurrently done. So it's not even a question. And this is how we can accomplish huge data centers around the world that can be able to sustain the kind of performance. By the way, there are 700 huge hyperscale data centers around the world today. So you can imagine how much power is cranking.
Yeah.
Just tell us, so what's next? Given where you are now, if you look out next 10 years, what do you see is coming, and how are we going to evolve in our as a computer architect, and as you've seen what's happening last 20, 30 years? What do you see the next change?
Well, I think what you're going to see, again, you look at the macro trends, right? And you see that, Moore's law is not dead, but it's not increasing at the rates. It's the flat part, we're not getting the power energy advantages that we used to get. We're not getting the cost advantages that we used to get. And so the innovate, but yet we've got this huge drive to provide more compute for machine learning and AI, right? So, as we talked about earlier, the sizes of the models are growing exponentially. The amount of compute is required for training these large models and for serving them to users is also growing exponentially. So, we're going to have to be more clever, right? And I've always said, it's about not taking the brute force approach, and I've never taken that. That's never been the way that we've seen success. It's about finding out how you can be clever, right? And so what does that mean from the algorithm point of view? It means, okay, how do we look at sparsity? How do we think about things that can be both specialized but also general at the same time? And that's what's going to win, right? It's not going to be, I'm going to take this algorithm and I'm going to cast it directly into silicon and get very efficient, because hey, the next minute some smart AI ML algorithm person will say, I want to do something different, and then your chip no longer provides the capabilities that you thought were interesting. And so there are some key ideas that we need to exploit. Data flow is one, sparsity is another, and thinking about how to do things in a more general way that can capture the full set of things that one wants to do in the data center, whether that be ML processing, or there might be SQL data processing, whether it be graph processing. I want to bring all of this together in one unified compute environment that can all be accelerated and all be fungible, right? And so 1 minute I want to do data processing, the next minute I want to do training using ML. The minute after I want to do something that could be core scientific simulation. Can we provide a single way of accelerating that is highly efficient and gets you close to what you would have gotten had you developed a specialized architecture? So it's about specialization, but then it's not. It's about how do we get specialized capabilities while retaining the flexibility that we all know and love. Right?
Yeah, I mean, this is how you can manage it much more efficient architecture and performance, right? And consistent performance. Yeah. The problem of the past was everything was kind of dedicated. Now we can be able to put it in containers and use it as need basis. And I think hyperscalers have shown a lot of those potential capabilities through data center, which of course can be optimized through better architecture that you're innovating over there. I want to change the subject a little bit about the lessons you learned, because you were clearly in academics, but you also had an entrepreneurship and you built some great companies along the way here. So what are some of the lessons you learned about how do you do that? I'm sure there's many professors out there and many entrepreneurs and many others want to try and figure out how to manage and be able to innovate. And the Stanford and Berkeley had been very special in creating a lot of new ideas that became, especially Stanford, creating a lot of companies that came out like a factory. And I just want to see how, what advice you can give to others.
Well, I always say you can find and work with the best people you can, right? And I think back to, the successful companies I've been involved in, and it's all been about the people, right? It's about, my co-founders on Afara Web Systems, Fermi Wang and Les Cohn, great people to work with, brilliant minds, technically brilliant minds from a business point of view. And then the team that we built around it, right? Early people like Punacha Kongadaria and students that came with me, from my lab that were early people. And so it is really about, getting the right team together, creating an environment that they can be successful in, and they can demonstrate, and then having an idea that is going to be different, right? And so, and then having the conviction to carry your idea through, right? And also, lots of academics have ideas, and either the idea is not quite, doesn't have the right elements, right? The right elements, and that it is both different enough and practical enough that it's going to solve a real need and meet a real problem, or they might have those elements, but they couldn't get the team together, right? That could really go and deliver something to the marketplace. And so you've got to bring those pieces together. And so that's what I think are the ingredients to a successful company. And then knowing your limitations, right? And then that part of knowing your limitations is getting the team around you to fill in those gaps in your capabilities. Yeah.
So it's all about being around great people.
Yeah.
Working with the right team, and then understanding your limitations and working on it, right?
Yeah.
No
Yeah.
Great. Excellent. This has been a really good discussion. I really appreciate your time for the speaker series, and I'm sure our audience will appreciate some of the lessons that you're sharing with us today. Are there anything else you want to talk about?
So, I mean, you've done a lot of work in sort of investing and identifying startups. What do you look for when you're kind of thinking about?
Oh, that's a good question. I have to say, I think actually my answer is not much different than you. I look for big ideas that can have a huge impact. And then I look at the person that are behind the idea, and the person or team have to be brilliant, because it takes a brilliant people to make a big impact. And then I think it's also, you have to look at the time span. Some great ideas, it's not that great idea is not right or wrong, just being too early or too late. So you want to look at timing. I think that's the most difficult part. So those three things are probably what I look at. And then, I just love lots being involved in great entrepreneurs and mine that are bring new things, because we are, I think through that, we can innovate, and innovation can have a very positive impact in our lives. Like what you've seen with your company, Migo, right? It is a very simple idea of phone data along with what the payment people may need, and combining those two. It's often multidisciplinary solution, but the technology is there sometimes. It's about putting it together, and go to market is usually very difficult. And that's the part that we have to look at very carefully. Yeah.
Exactly. The go-to-market component is one that you definitely need help with as an academic, right?
Right. Yeah. A lot of great ideas, but if you don't know how to sell, how to market, how to solve the frictions you talked about. So this is what I always look at. Can you solve those problems?
Structures. Yeah.
So I have this idea of NABC, and N stands for what are the critical needs, right? What are the problems? And then A is approach. Most companies come with approach, not thinking about, does it really solve the big issues or not? And then B, what are the benefits to consumers or customers or partners and your employees, and maybe even the sustainability perspective. And then C would be competitive options. What are the alternative options? So you have a great idea, but if there's a much cheaper way of solving the same problem, maybe that's an issue that you're going to have. So NABC is the framework that we use, and make sure we understand that environment, and then make decisions and support the entrepreneurs like hell, and hopefully it goes somewhere.
Yeah, great.
Well, Kunle, thank you very much for your time. Really appreciate the conversation today, and you have a great day.
Well, thank you, and thank you for all the good questions. Great.